Hi and welcome to this video series on the exploding wire. Today I'm going to talk about some of the topics on this exploding wire project and things that I learned when I was working with the exploding wire experiment in the summer. So the exploding wire is a quite dangerous thing, and you can see in this cluttered slide that we have a lot of things that we should think about while doing the experiment on the exploding wire. We have safety concerns for the operator, so you don't want to die from high voltage bursts. There are some ultraviolet radiation. There are obviously blast sounds. We don't want to damage the equipment, so we want to make sure that the cameras and oscilloscopes and whatnot, these pretty expensive equipment, stays with us during the experiment. So and here we have this thing that is kind of scary because it looks like action at a distance. So at high frequencies, stuff begin to couple magnetically or capacitively, and also radio waves and electromagnetic pulses begin to fly in the air, and these things can interact with the sensitive electronic equipment and damage it, even though there is no physical connection to it. So this is one of the scary things about electrical engineering that I guess we should be aware of while performing our design on this experiment, and it should actually guide all of our actions while we're doing the experiment. Also, we have some practical concerns on the design, so we want to make sure that the design is sized adequately. So we don't want to blow up the lab, but on the other hand, we don't want to make the explosion so small that it doesn't do anything or it doesn't enable us to study whatever we want to study. We want to make sure that we convert the electricity stored in the capacitors into blasts, and the exploding wire is just a tool, right? So, but we want to make sure that we can actually make the electricity be converted into a shock wave. Also, we have a problem with high frequency electronics, which concerns about the data. So you're gonna use some sort of device to measure stuff. So even it can be a camera, it can be pressure sensors, it can be something connected to an oscilloscope. And because we're gonna use cables to connect these things together, these cables are subject to electromagnetic pickup, and this pickup can generate a lot of noise, especially if the cable is pretty long. And long, I say like 1 meter long. So basically any cable can pick a lot of electromagnetic radiation, and since we're generating an EM pulse from the exploding wire itself, the measurement that we take might look like something, but it's just electromagnetic pickup from the dangling wires that we have in our experiment. So we want to make sure that these things are controlled, so we can actually collect good data from out of our experiment. So I'm going to talk about these three topics, which are the topics that I focused in Dr. Larson's lab. And in order for you to appreciate, I'll have to talk about electronics, because the exploding wire is an electronics project. We want to make a blast, but the blast is generated by the capacitors, and therefore we need to understand very well what's happening in the high voltage electronic side, and we cannot neglect this. There are a lot of weird stuff happening, and we need to make sure that we understand it. And because it's a fast phenomenon, so we are talking about the entire phenomenon is over in less than a microsecond. So we want to make sure that we understand what's happening in the high frequency domain, because things begin to behave weirdly in high frequencies. So I'm going to talk a little bit, very skimming through about this. So the two components that play the major role in high frequency are the capacitors and inductors. And so what's a capacitor? You probably remember from your physics class, the capacitor is just a couple of terminals. Sometimes they draw it with two plates, right? And basically, it doesn't need to be two plates. What actually matters is that we have some sort of insulator here that prevents the current from passing through the capacitor, right? So current cannot pass through the capacitor because it's isolated. But it doesn't mean that charges cannot accumulate on the sides of the isolator. Imagine that we have this capacitor and it is being charged. So while it's being charged, the charges must arrive at the terminals of the capacitor, and therefore we have a current, right? We have charges moving towards somewhere. So this current here that is generated by the charges while the capacitor is charging, and in the other side we're going to have current going away, right? So these charges here, they look like a current is virtually passing inside the capacitor. And because of this virtual current that is inside the capacitor, and we know that there is a voltage across the capacitor, there is a sort of voltage drop caused by the capacitor, and this thing is like a resistor behavior. And this is what electrical engineers call impedance. So if we increase the frequency, the capacitor looks more and more like a short circuit, and so this is why I said here that in DC current we have an open circuit, but as we increase the frequency, it might look like a short circuit. So this is the mathematical correlation. We have J here, which is the square root of -1, and we have 2 pi Fc showing that the dependency is inversely proportional to the frequency and the capacitance. So for the inductors, we have the very opposite behavior. So the inductors have an ever-increasing impedance. And what does it mean? So while we run a current through an inductor, what happens is the current generates some magnetic field, right? So we know that there is a magnetic field that surrounds the inductor. And this magnetic field B will surround the inductor as long as the current is constant. But when you change the current through time, maybe you want to, for example, so maybe you have a switch over here, and then you open up the switch, and while you open up the switch, you basically are turning, you want the current to stop, right? But it can't stop because the magnetic field is already there, and it is basically pulling the electrons. So while the magnetic field is still there, it will pull the electrons. And as it pulls electrons, they accumulate on one side, and then less and less electrons come up, and then eventually the magnetic field dies. Sometimes it rings, but what actually means is that we have this inertial component. So the inductor is an inertial component for the current. And so as we want the inductor to respond faster and faster, it will do less and less. So when we are very slow at DC current, we have a short circuit. It will respond very well, but as we increase the frequency, it might look like an open circuit. So basically the impedance, ZL, is proportional both to the frequency and the inductance of the inductor. So a large inductor will have more inertia, which makes sense. So what does it mean in reality, right? So this is a snapshot of an exploding wire experiment that we were working with. And we can see here basically we have a capacitor bank over here, and we have 2 copper bars, 2 copper strips that connect the terminals of the capacitor to the exploding wire. And this system here, it's pretty easy to identify that there is a capacitor here because it's supposed to be a capacitor. It looks like a capacitor, it has a function of a capacitor, it's supposed to store charge. But what's not so obvious is that these copper strips here are inductors, and they are the only inductor, roughly the only inductor in the circuit. They are the largest inductor in the circuit, and because they are the largest inductor, they will behave as an inductor in the circuit. So we can draw the circuit as a capacitor connected to the exploding wire through 2 inductors. So these 2 inductors will do something, and this is not trivial. You look at the copper strip, and it doesn't look like an inductor. It's not wound around. So it's not it's tricky at the first glance. You might look at it, it's just a wire, it's just a copper strip. It's not doing anything, but it's doing something. And this is where the danger lies, because so I placed here the same circuit. The values are measurements that I made during this experiment, and you can see we have this handy-dandy equation for the impedance of the inductor, right? So if we replace the values of the frequency with the resonant frequency of the circuit, which is roughly 200 kilohertz, and the inductance of the inductor with the value of the inductance of the inductor, we have an impedance for each inductor of 0.31 J ohms. And this impedance here is for each of the inductors. So now if we take a look at this circuit, we can see that the inductor has a way larger impedance than the wire itself, which means that the inductor will predominate the behavior of the system, at least in the beginning. So if we have, let's say that we have the capacitor charged at 20 kilovolts, and here we have the ground wire, and we are using this as a reference voltage of 0 volts. So imagine now that we want to naively try to measure the probe. What is the voltage drop in the resistor? So we place our probe across the resistor. So this is a high voltage probe. It has a voltage divider here. You can see 990 meg ohms and 10 meg ohms. So this is going to divide the voltage by 1,000, a factor of 1,000. And because it's dividing the voltage by 1,000, you might think, well, that's fine. It's dividing 20K by 1,000, right? So we're fine. It's going to have 2 volts here, right? That's what you think. But what is not so obvious is because we have these 2 extra impedances here, they will have a voltage drop across them. And it's pretty easy to see that since this is very small, we might as well neglect it, and therefore there is going to be a voltage drop of 10 kilovolts in each inductance. So we're going to have a 10 kilovolts potential here in this point. And now it's kind of easy to see how dangerous this is, right? So imagine that we connect our oscilloscope to this high voltage probe. So there it is, our oscilloscope. And most oscilloscopes have the ground terminal connected to ground. So this here is at 0 volts potential too. But it can't be, right, because it is at 0 volts and 10 kilovolts. So it can't be at both voltages. So what's going to happen is that we're going to have we have a very small resistance in these leads that connect the probe to the oscilloscope, right? So this very small resistance will cause this voltage drop. So we're going to have a huge current running here, and it's going to run all the way to ground. So this is quite dangerous, right? Also, of course, this is going to happen for a very short amount of time, just the amount of time when this current is running. This is a very crude simplification. You can do your simulations and see what's going to happen. It's going to have a voltage waveform. But what is important here is that in this very notional view that I'm showing, if we have devices connected to the USB cable, which was the case for our experiment, this is a mistake that we committed. So if we had things connected to this USB cable, the USB cable is also connected to ground. So we have a potential of damaging equipment here. And that's actually what happened. So we lost all this equipment here because of this quite naive mistake. So this is the reason why I'm emphasizing so much on this particular problem. So another thing that is very important is the transmission line theory. So I'm gonna again skim over a little bit in the transmission line theory. This is a very complicated topic, and it is a science on itself. But some pitfalls and caveats that the transmission line theory plays on us here. So basically any piece of cable or something that transmits a signal is a transmission line. And what is the transmission line? So we have here an RG58 coaxial cable. You can see here we have this core wire that transmits the actual signal, and we have a ground wire here that acts as a shield for the coax cable. And we have something here that isolates the core and the ground. So we have some sort of isolator here. So since any piece of wire is an inductor, and any piece of insulator is a capacitor, we can see here that the transmission line, this coaxial cable, is actually two inductors connected to by a capacitor, right? But since both inductors and the capacitors are continuous, it's not that easy. It's like the capacitor is connected everywhere. So in order to model this, what electrical engineers do is this sort of circuit where we lump a little piece of the transmission line, as you can see here, and we basically make this as a dx of the transmission line, a very small piece of the transmission line, and then we duplicate this all the way to the length of the transmission line and integrate to get the properties that we want to take from the transmission line. So this is what transmission line theory tells us. And the interesting thing about the transmission lines is that they can act as waveguides. So this thing at very low frequencies, it's going to just transmit the signal, right? But we know that the signal cannot transmit at infinite velocity. There is a speed limit. This should be the light speed or the light speed through this thing, right? So there is a limit for this electromagnetic wave to transfer inside the wire. So this speed limit is very simple to calculate actually. You can derive from the circuit, but the thing here is that since it's a waveguide, it's gonna resonate. It's bound to resonate at some frequencies, and it's gonna depend on its length. So the longer the transmission line, the more it's gonna have some effect on the signal that we wanna measure. So this transmission line have a transfer function that looks like this. So we have in low frequencies we have an inductor-like behavior where the impedance rises as the frequency increases, so increases as the frequency increases, but there is a frequency where it resonates, and this frequency is exactly at a quarter wavelength, and of course the length of the cable equals to lambda over 4. And we're gonna have an anti-resonating point at lambda over 2, and then a resonating point at 3 lambda over 4, and so on. So we have this interesting behavior from the transmission line, and this can alter the behavior of our signals while we're doing measurements. So that's the reason why this is so important. It might actually change the signal that you're measuring. So how do we prevent the signal from being changed? So we need to do something called termination. So termination is called by the electrical engineers as placing something in the end of the transmission line that looks like a long piece of transmission line, so it will not reflect anything. So this piece here is a resistor. Normally it's a resistor, and it's pretty easy to calculate the resistance. Actually, for example, for the RG58 transmission line coaxial cables, we have a 50 ohm characteristic impedance for the transmission line, and you gotta be aware that this is something that you might want to do, because imagine this wasn't here. Imagine that there was no termination, and then we generate some sort of pulse in the source. The pulse travels through the transmission line, and then we're gonna measure it on the oscilloscope. But if we don't have anything here, then we have an open circuit, and an open circuit, by definition, it will reflect everything in the pulse. So it will reflect everything. So the pulse will travel back, and it will arrive at the other side with some time delay, right? Because it's going to travel the whole transmission line, the whole length, and it's going to arrive with some time delay. And then we're going to have this pulse that has this, that's going to be the sum of these two pulses. So when we measure the pulse actually in the oscilloscope, we're not going to measure this clean signal, but we're going to measure the sum of the two pulses. So it's going to be something weird. And because of that, it might actually alter the way the signal is, and we might be taking wrong measurements. So that's the reason why, especially in long pieces of coaxial cable. And one thing that I saw in the lab is that since we placed the exploding wire very far apart from everything, so it doesn't blow up everything, we actually make the coaxial cables very long, and because of that we might have this thing, and that's the reason why it's so important. So in the next video, I'm going to show a short clip on what does it actually mean, and actually I'm going to perform the measurement of the length of a piece of coaxial cables, so you can see this problem in practice and get a little bit of understanding of what's actually happening. So thank you very much for watching this video, and bye bye.